Okay, good morning and welcome back. And this is the first of a series of videos which I would call question and answers. And in this video, I'll try to address questions that have been raised either through the Telegram chat of the course or by email or on the link below the lectures, and try to be more specific about parts in the lectures where I probably have been a little bit too superficial. So I've been asked specifically to comment a little bit further on how can you resolve and access ground state information from long-time imaginary time, quantum propagators. So let me go over that point again in a little bit more detail. Suppose I'm evaluating the quantum propagator between 2 points. Let t be the imaginary time. Actually, let's call it tau, just to remind myself that this is an imaginary time, starting from some initial position. And we know this is actually can be written as a in imaginary time can be written as follows: SE is the Euclidean action of the path, and let's suppose we can evaluate this by Monte Carlo. Actually, this is not the easiest object to evaluate by Monte Carlo because it corresponds to a partition function rather than to an average of an operator. There are ways you can do that, but they are a little bit more involved. But for the point of view of conceptual understanding, I will stick to this calculation rather than going into more sophisticated quantum Monte Carlo formalism, because that is not the base subject of this course. So for the time being, let's suppose we can evaluate this object through Monte Carlo, which in many cases is actually possible. So how does this calculation lead to any ground state information, and how do I exactly extract the ground state information? Well, the way to do that is to remind myself that this is actually written in the following way. That's the quantum Hamiltonian, that tau is the Euclidean time, x naught is the initial position. And like I said in the course, I stick in the complete orthonormal set of states which come from the eigenstate of the Hamiltonian. I have already replaced the eigenvalue of the Hamiltonian in this position here. And then this will become a sum over wave function star of the nth state at point x multiplied by wave functions at point x naught. For instance, if I choose x naught to be equal to x, I have the square modulus of the wave function of the nth state weighted by the negative exponent of the eigenenergy in units of h bar times the Euclidean time. Now, like I said in the course, I expect this sum in the limit of very large times to be dominated by a single exponent, the ground state exponent, because all other terms will be exponentially suppressed with respect to this. That's the exponential corrections. So let's suppose, to make this explicit, let's take the logarithm of this object. So if I take the logarithm of this guy, and maybe I'll do that by erasing this part of the whiteboard. If I take the logarithm of k and I take a negative, well, let's take the logarithm by itself. Logarithm of k as a function, let's consider k as a function of time only, keeping x naught and x fixed for a moment. Well, I look at this formula down here, and this will be the logarithm of psi naught star of x, psi naught of x naught, times e to the negative e naught over h bar tau, which means that if I take the logarithm and I use the properties of the logarithm, this is the logarithm of the wave function product negative E naught over H bar tau. So now you see that if I plot this propagator here in logarithmic plot as a function of linear time, I expect that for large times, where after have filtered out all the excited states here, in logarithmic plotting, this correlation function should scale like a negative straight line with a given slope, which is E naught by H bar. So, being more specific, I can either use logarithmic units or I can plot the logarithm of k. That's basically in linear units I can plot the logarithm of k as a function of time, essentially the same thing. And typically what happens is that I have an intercept, but if I wait long enough time, my logarithm should become a straight line. My logarithm of correlation function should become a straight line. I'm realizing that this line is not visible in the screen. That horizontal line is not visible. Let me draw it. This is time, Euclidean time. So from this slope, I can actually get access to E naught in units of H bar. And the intercept provides me information about the logarithm of the wave function in 2 points. On the other hand, this area here is the transit area where the correlation function is dominated not only by the ground states, but receives contribution from all the spectrum. And this is the area where really it is very difficult to make any statement, because your signal is contaminated by the presence of multiple eigenstates in a way that is very difficult to disentangle. Actually, there has been in the last 40 years or so a huge activity in trying to make use of this information, extracting information about the excited states. But it turned out that this operation, because of the properties of the Laplace transform, essentially, there is a Laplace transform involved in the relationship between the spectral density and the correlator. Because of the properties of the Laplace transform, extracting information about excited states from this transient area is exponentially hard. Basically, it's a hard problem. And there have been some progress, even some remarkable one. The Trento group in nuclear theory has developed a very smart and efficient way of dealing with what is called the inverted problem of extracting spectral information from correlation functions. But in general, it's just very hard. So the standard information that people get out in a very convenient and economic way from this kind of calculation is really about the ground state. I hope this was clearer than it was in the original lecture.